All right, so let me show you how the slope of a tangent line comes about. We're just going to use this function y equals x squared as an example. So over at 2, there's a point at 2, 4. So I want you to recall that back when I just did a rough sketch of the tangent line, I was just briefly introducing you to what a tangent line does and what we're looking for. But remember that if I'm at one single point here, I'm not really sure. Does the tangent line go this way? Does it go this way? I've got to be a little bit more specific. So what I'm going to do instead is go through the formal theorem and how it came about. So right now we know there's a point at 2, 4. But I need 2 points to technically find the slope. And the second point is going to come from the line you drew. Again, I'm going to repeat it. I don't really know where exactly the second point is going to come from. I mean, I could try to guess. So what I want you to do is I want you to think about this graph, this function being extended. And then let's say that I connected from this point to, let's say, this point up here. So my line, it's not a very good drawing, but my line that I drew goes through this point and it goes on the inside of here and then comes back out. So what we have now is called a secant, S-E-C, secant line. Don't get this confused with secant on the unit circle. Two totally different things. A secant line is just a line that intersects a function in 2 spots. Kind of like a tangent line is one that hits it in 1 spot. A secant line hits it in 2 spots. So what I'm going to need is I'm going to need 2 coordinates. And I know one of them is 2, 4. And the other one is somewhere, we don't know. I know it's to the right of 2. Do you know how far to the right of 2 we went? No. So what I'm going to do here is I'm going to do a little squiggly and call this delta x. Remember, that's the change in the x value. So then this point here would be called 2 plus delta x, because it's delta x on top of the 2 that was already there. Okay, now the y value here, again, I don't know it, so it's going to be f of the function's answer when I plug in 2 plus delta x. Alright, so now let's go and talk about the function. So 2 plus delta x. Now, how do I get the function, the y value? Luckily, I already know the equation for the function, so I have to do 2 plus delta x all squared. So now if I go to find my slope, remember I'm going to be doing y2 minus y1. So y2 is going to be 2 plus delta x all squared minus 4, because remember 4 is right here, over 2 plus delta x minus 2, because that was my x value. So this is my y value minus my y value, and x minus x. So let's simplify that. Let's expand this. And then we're going to simplify. Those are going to cancel. These will cancel. And I can factor out a delta x. Those cancel. And I'm left with 4 plus delta x. Okay, so now we have another slight problem. I was trying to find the slope, right? So what we're doing here is we're starting off with a basic idea of finding slope between 2 points. Okay, but now as this point gets closer and closer and closer to this point, my line is going to then become a tangent line. So you're moving from a secant line to a tangent line. So what we're doing is we are taking the limit as delta x approaches 0 of this function. So at this point, now I'm going to plug 0 into here, and I'm going to get 4. So now I'm saying that the limit as delta x approaches 0 equals 4, which means that the slope equals 4. Now, what does all this mean? Hopefully you kind of recognize some of that work there. It means that when we take the limit as delta x approaches 0 of a function's change minus the original function, all over delta x, that should look familiar, that is actually going to give us the slope. And in a few minutes you're going to talk about what the slope means. Slope is going to actually mean the derivative of the function. Alright, so let's take a look at the next couple problems. Alright, so in this problem it says, at what point is the tangent to this function going to be horizontal? Well, let's take a look at the function first. So let's go ahead and sketch it. We're going to go ahead and sketch it using our graphing calculator. Something like that. Forgive my little sketch. So in order for the tangent, this is vocab terminology now, in order for the tangent to be something, tangent should ring something in your head. Tangent means slope of the tangent line. And we want it to be horizontal. So we're asking for when we're going to draw a horizontal tangent line. So just by a visual, where could we draw a line so it hits the function one time, but that line's horizontal? It would be at the vertex. And again, this picture is not the best. Look at the picture on your graphing calculator. So we need to figure out, where is the vertex going to be? So we're going to go opposite of B over 2A, opposite of this, 2 times this. So we're going to get 4 over negative 2 is going to be negative 2. So we know it's going to be at negative 2 something. Now plug the negative 2 in. So now we're going to go negative of negative 2 squared minus 4 times negative 2 plus 3. That would give us 4, but there's a negative out front. That gives us 8 plus 3. That gives us 4 plus 3, and we should get 7. So at what point will we have a tangent to the function being horizontal? At this exact point. Alright, our last example here says the accompanying figure shows a distance and time graph for a wrench that fell from the top platform of a communication mast on the moon to the station roof that's 80 meters below. Find the slope of the secants. Remember, secants are just when you connect a line and it goes through your function twice. So they want us to connect P to Q1. So here's P, here's Q1. I don't have a ruler on this program, so I'll try my best here. So they want us to find that slope. So from P to Q1. So we're going to, granted these are going by tens, right? 10. Alright, so I'm just going to do rise over run. So P and Q1. So we're rising 10, 20, 30, 40, 50, 60. And running 1, 2, 3, 4, 5. So my slope between those two that are the furthest away from each other is 12. Alright, now let's find the slope between P and Q2. So we're going to go 10, 20, 30, 40. 40 over 1, 2, 3. Three goes in 4 ones with 10 left or 1 left over, 3 and a third. All right, now let's do P to Q3. So noticing as the point is getting closer and closer to our actual point, our secant line is becoming more almost as if it's a tangent line. So from here on up, it looks to be about, I would say 56 up, so about 24, and going across about 1.5, so that's about 16. And let's do the next one now, P to Q4. So now if I connect these two, notice how it's almost a straight line. That almost looks like a tangent line because these points are getting closer and closer to each other. probably about 72-ish over a half of a unit. Why did I put 72-ish? The distance from 72 to 80 would be 8. 8 divided by 0.5 is about 16. So what's happening is it's a bigger jump, and then eventually the closer and closer they get to each other, the slopes are going to start leveling off. So eventually what's going to happen is the slope would just eventually limit out to about 16. So part B says now let's estimate the speed at the point P. Then we're going to say, since the last two were about the same, we're going to say that we are approximating a speed of about 16 meters per second. So again, what we're showing you here is taking the slope of secant lines as the second point gets closer and closer to our point of question. Our secant line turns into a tangent line, and then the tangent line will give us our slope, our rate.